Hello, this is Dr. Lori. Welcome to this next segment on standard deviation versus standard error. If you remember, when we had individuals in a population, we could graph, very often we could graph a scale variable as a normal distribution. And so imagine that each person inside of this distribution is just an individual, and we've measured some variables such as height or cholesterol or something like that. So those variables tend to eventually kind of be spread out. What we'd like to look at in this particular video is to see the relationship between sample size and hypothesis testing. So let's imagine that we are taking repeated samples of size n equals 4. So out of this population, we draw 4 people at random, and then we put them back. For each sample, we calculate the average. We would expect, just by chance, that half of those averages would be above the population mean. So let's go ahead and put that on here, and that's going to be somewhere right here around the middle. So here we have our population mean. We would expect half of the averages to be above mu, and the other half of the averages, these averages that we calculated for each of the samples, to be below mu. So we've drawn a bunch of samples with sample size n equals 4, and then what we can do is we can graph them onto a distribution. And this is approximately what those would look like. And in our last video, what we discovered is that the mean of these samples has an average that's the same as the population mean. So this is the m sub x bar. So it's the mean of the means, which can start getting confusing after a while. The thing that I would like to add, and we learned that this distribution has a special name. It is called the sampling distribution of the means. And so here we have a bunch of samples, and they have their own distribution. That's supposed to be a vertical line, sorry. So here we have graphed it. It ends up looking like so. And if you remember, in our original population, we had kind of an area here that represents 95% of the whole area under this curve. So this middle part is 95%. Well, this sampling distribution of the mean also has that same idea, where we have this middle area, and that represents 95% of the time that it falls in that area. This is approximately plus and minus 2 standard deviations. This is minus 2 standard deviations. The same concept applies here to the sampling distribution of the mean. Here we have 2 of something away from that mean sub x bar. And we call it a different name. Here we've called it standard deviation, and down here we call it standard error. And so when we've created a sampling distribution of the mean, what we do is we still graph it along the x-axis. We find that the means are equal, but it's not as spread out. And the not as spread outness of it is regulated by an equation. So let me give you that equation. Standard error, let's get SE. So standard error is equal to standard deviation divided by the square root of n. And so in this case, our sample size n was equal to 4. So let's imagine that our standard deviation up here is equal to, say, 60. So here's one standard deviation of 60. Here's two standard deviations, so that ends up being 120. Also, same thing happens below the mean. Plus and minus 2 times 60, approximately 2. And so in this particular case, if we wanted to calculate the standard error, that would be equal to 60 divided by the square root of 4, which is equal to 2. So 60 over 2 is equal to 30. Now, one of the things that you'll find is that when you're in a testing scenario, and I'll do this for you as well, oftentimes we'll provide you with square roots and calculations that can be done easily in your head. And so just about anybody can divide 60 in half and get 30. Most people can take the square root of 4 and get 2. And so let me just remind you of some of those common numbers, just so that we're all on the same page. We want to get rid of that. Here we go. So we can scroll down. Oh, it doesn't want to let me scroll. I'm going to have to write it in the top right corner. Okay, so here we go. Let's say that we have a bunch of numbers, 2, we'll get rid of that. My pen is acting up. 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what is 2 squared? We'll put SQ for squared. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 36, 49, 64, 81, 100. So if you see sample sizes in any of these numbers, so if you see a sample size of 36, you know then that if you're trying to calculate something like this square root on the bottom, that you can take the square root very easily. So SQRT. We can take these sample sizes and convert them back to their square roots, and so that's why these numbers are used so frequently. Sample size of 100, square root of that would be 10, and so forth. And so that's just kind of as a reminder. One of the things that I would like to point out about this is that even with a sample size of only 4, that this is much narrower than this is. In fact, if I drew it even somewhat to scale, it should be about half as wide. And so if this is 1, 2, 3, 4 across, this should be 1, 2. Didn't draw it quite to scale. So, and you can see then with the sample size that is even more than 4 as we go up and get higher and higher sample sizes, what happens is this distribution, let me find another color, maybe yellow. This distribution gets even narrower and narrower. So with increases in sample sizes, we get more and more and more sure of our results. So as sample size goes up, I'll just draw this, increase in n, that leads to a decrease in standard error. So standard error goes down, it gets narrower. That sampling distribution of the mean gets narrower and narrower. Thank you for joining me for this topic.